The regression analysis is an often used statistical method to find relationships between variables. In this lesson, we'll take a look at the regression analysis. Enjoy! The regression analysis is one of the simplest ways to make a prediction. If you take an outcome variable and you have a predictor variable, maybe one, maybe multiple, and a number of control variables, you can use the least squares technique to estimate the relationship between the data points. When we talked about correlation, we talked about Pearson's R. In regression, R squared represents the fit of the model. So the R squared that we already saw in the correlation analysis will, in this analysis, return fairly similar, especially when we control for the same control variables that we also controlled for in the correlation analysis. Here you see an example about the relationship between age and pay. And what you see when you connect the dots is that when someone gets older, they get paid more. And pay is a monthly pay in dollars per month. So what the regression analysis does is it tries to calculate the line that has the least squared distance between all the data points. And you see that here. You see a line that's drawn, and the distance between the points, for example, at 25, the distance is about $300 in pay. This is squared and it's done for all points. And the curve, or in this case the line, because we're talking about linear regression, the line that has the lowest value, so the least squared, so the lowest distance between the line and the points squared, represents the best fit for the model. So in this model you see that with every 10 years someone gets paid around $1,200 per month extra. So when someone is 20, it's $2,500. When someone is 30, it's $3,700. And when someone is 40, it's $4,800. And using this same logic, using this line, you can prolong it and you can say, hey, what would be an estimation of when someone is 50? How much would a person earn per month? If pay increases with $1,200 every 10 years, that's around $120 every year, then the difference between 40 and 50 will be $1,200 extra, so someone will earn approximately $5,900 every single month. This is a very simple example of just two variables, age and pay, and seeing, hey, given someone's age, can we make a prediction of how much that person is paid? Let's take a look at our dataset, the same dataset that we use for the correlation analysis. We see age, gender, performance, and engagement. What we want to know is how engagement, the independent variable, influences performance, the dependent variable, and how gender and age act as control variables in that relationship. Because in the correlation analysis we included both variables as controls, but we didn't really know whether age had a big effect or gender really had the big effect. And in the regression analysis we'll actually find this out. So what we do is we click Analyze, and we don't go to correlation, we go to the regression, and we select the linear regression. So in our dependent variable we select performance, our independent variable is engagement, and we click Next because we want to include two more control variables. And in the control variables we include age and we include gender. In our statistics we say, hey, give us the R squared change, because that will help us indicate which explanatory model fits best, which control variables we should actually use, and the descriptive statistics, because we looked at that last time as well. So I click OK, and the regression analysis shows the descriptive statistics with performance with a mean of 3.7, engagement 3.75, similar standard deviations and the sample size. We see the correlation matrix with performance and engagement correlating with a correlation of 0.35 as we saw previously. And then we see the three different models. The first model just has engagement as a variable. In the second model, age is added, it's entered. And in the third model, gender is added as well. So those three models are summarized over here. And what you see, the first model has a high number of F changed. And F is a representation of the explanatory value of the model. So if f significantly changes, that's a good sign, and you should include this specific variable. So what we see is that for the first model, we have a significant change for f, so engagement does a better job in predicting levels of performance compared to not including engagement. In the second model, when h is entered, we also see a significant change of f, which means that both engagement and when h is included, h also improves the model in a significant way, so we should also add h to the model. But when we then enter gender, we see that f doesn't change significantly, so the third model doesn't really add explanatory value, so we should leave that one out. So we should focus on the second model because that model works best. So how does that look like? And this is the correlation coefficient. We see when we correlate engagement with performance, a beta of 0.35, which is exactly the same as the correlation between performance and engagement. Additionally, we see that a 1 point increase in engagement leads to a 0.4 increase in performance in this specific model. And it's highly significant. In addition, when h is, let's pop it out, when h is added to the model, we see a b-value of 0.01, which means that when age increases by 1 year, someone's performance increases by 1/100th of a point. When age increases by 10 years, so someone goes from 20 to 30, someone's performance increases by 0.12. And again, we see a highly significant value, so both engagement and age influence and act as predictors for someone's performance. So when you know someone's age and someone's engagement level, you can actually make a prediction about how they are likely to perform. And we're left with a value of engagement where if engagement increases with 1 point, performance increases with 0.35. And by the way, keep in mind performance is measured on a 5-point scale ranging from 1 to 5. So a 1 point increase in performance is 25% of the full range of performance. So if we can attach a financial value to someone's performance evaluation, to someone's performance rating, we know we have an indication of what a 1 point increase in engagement can result in terms of a financial effect. So this is a more detailed look at how engagement impacts performance, and we learned that age is an important factor in terms of how someone performs, but someone's gender is not an important factor. Of course, this is a slightly simplified example. For example, if we want to see a real cause and effect relationship, we want to measure engagement and performance over time. So we want to measure engagement on this moment and engagement, for example, in half a year or in a year, and do the same for performance and then see, hey, does engagement now predict performance in half a year or in a year? That's the proper way to determine a cause and effect relationship. The only thing we do now is building on literature and saying, hey, in literature we see a cause and effect relationship, so we assume that the relationship between engagement and performance is also a causal relationship. But to find this in the data, you need to do more advanced analyses. And in addition, you'll probably also want to correct for different store locations, for different departments where the people work on. These are all control variables that you want to add in your model. But I think this was quite a nice and simple example of how fairly easy it is to do an actual analysis. And again, like I said the last time, most of the time is in the preparation and the aggregation of the data, not in doing the actual analysis.